My name is Shanaz Abraham. In this video, I'll be presenting my lab on creating the orbit of a star around a black hole. The purpose of this lab was to simulate a star orbit to determine the mass of an unknown black hole and then design a stable figure-8 orbit for a spaceship around a planet and its moon. This lab explores Newton's law of universal gravitation and Newton's second law of motion. The net gravitational force between two objects depends on their masses and the distance between them, which is expressed by F equals G mass 1 times mass 2 divided by R. Using this, we can estimate the black hole's mass based on the star's motion. This experiment is divided into two parts. The first part was finding the mass of the black hole. I used the given starter code and Glow script and replaced the dummy email with my own to generate a unique star trajectory. Then, for each data point, I collected the net gravitational force on the star, assuming the black hole is located at the origin through the code. The time step between each position was 1 Earth day. Here is a code that has the equations we use in order to find the mass of the black hole at each data point. Each pass through the loop gave slightly different black hole mass values due to the rounding and orbital motion. To get one consistent estimate, I averaged all the calculated values. My final estimated mass of the black hole was approximately 9.96 times 10 to the power of 33. What does this mean? The net force and the rate of change of momentum are closely related. The net force points toward the center of the black hole, while the momentum vector changes direction as the star moves in its own orbit. The perpendicular component of momentum change alters direction, while the parallel component would change the star speed. This relationship explains why the star stays in orbit rather than spiraling in or flying away. For the second part, the purpose was to simulate a planet-moon system and attempt to create a figure-8 orbit for the spaceship. The planet was stationary at origin and the moon orbited in a circular path, and the spaceship started on the moon's surface. In the calculation loop, I determined the gravitational force on the moon due to the planet and the spaceship. By using Newton's second law, I updated each object's velocity and position. The challenge was finding an initial velocity that allowed the spaceship to orbit both the moon and the planet without crashing. After testing several values, the initial value that worked best was approximately 27,000 meters per second in both the x and y. This velocity let the spaceship loop around both bodies in a smooth figure-8 trajectory, influenced by gravitational fields. In my simulation, the moon's orbit appeared as a cyan circle, while the spaceship path was a magenta figure-8 curve. I confirmed that the spaceship speed remained well below the speed of light and did not crash into the moon. If we wanted to predict the motion of the entire system, the black hole, star, planet, moon, and spaceship, we would need to include all mutual gravitational interactions. The dominant interaction would be between the black hole and the star because of their massive sizes, but the planet-moon spaceship system would add smaller secondary effects. In summary, I used simulated motion data to estimate the mass of a black hole and then explored how to create a figure-8 orbit for a spaceship around a planet and its moon. This lab demonstrated the predictive power of Newton's law and how gravitational interactions shape orbital motion. Thank you for watching my video report.